Good afternoon, everyone. So this is the QEEE session on electromagnetics. Uh, yes, this is getting projected today. So this is the third of the QEEE electromagnetic session. The first session we had a module on transmission lines. The second QEEE session we talked about electrostatics and magnetostatics, and all the way up to the point where we derived all the Maxwell's equations and the boundary conditions. Now this is the third session that is going on. My name is Deepa Venkatesh. I work in the electrical engineering department of IIT Madras, and I had done these two sessions earlier. So what we have today, tomorrow and day after is a session on electromagnetic waves. These two are completed. This is the current session on electromagnetic waves, which we will do over 3 days, 2 hours each in the afternoon. Now in this particular topic, what we will do, this is the quick plan for the next 3 days. We will do a review of Maxwell's equations. So I would not be deriving them in detail, but I will tell you what those equations are and try to tell you why are they significant, what is the physical significance of each of those equations. For details, you might want to go back to my previous session on electrostatics and magnetostatics. Then we will go on deriving the wave equation. We would derive the wave equation for perfect dielectrics. Then we will do wave equation for lossy dielectrics. Further, we would do wave equation for metals or plasma or conductors and discuss the concept of skin effect. And we will end the current session with a discussion on Poynting theorem. This is the agenda for 3 days, which would have been conveyed to your colleges, and Poynting theorem we will also talk about power flow. So these are the topics that are going to get discussed in this session today, in the session for the next 3 days. What I would request you to do is, I have given the lecture notes to the colleges. So if the college coordinators can share the contents with the students in advance, they can read and come for these lectures, so that will be more useful. So what is given to you already are some lecture notes. I've also given a tutorial, which are basically problem sheets, and I've also given some multiple choice questions, MCQs. So I would request the coordinators to share the lecture notes at least. Tutorial and MCQs you can use as per your convenience in your respective colleges or universities. So as we go, I will also try to solve some of the tutorial problems so that it is easier for you to follow. Unfortunately, in this session, You cannot interrupt probably in between, but after every half an hour or 40 minutes, I will keep the session open to questions. So at that time, you please ask any questions or concerns or doubts that you may have from the content that we did. So we are going to start today. Most likely we will do the review of Maxwell's equations, and we will try and see if we can get to this point where we are deriving wave equations today. Tomorrow will be these two definitely, and the day after would be Poynting theorem, and if there are anything left over, we will do it on the day after tomorrow session. So to start with, let's start the agenda for today. The learning outcome for today would be to remember, appreciate, understand what Maxwell's equations are and what is their, so this is the agenda for today. Maxwell's equations, a review, and some physical significance, some points of application for Maxwell's equations. So Maxwell's equations as such are the pillars of electromagnetic theory. But before we start off with the pillars of the electromagnetic theory, we want to know what is the sand and cement that makes the electromagnetic theory. So what is very fundamental to electromagnetics is the concept of charge, electric charge. Because if the charges are stationary, a stationary charge is a source of electric field. This is something that you have been learning since your high school, that if I have a positive charge, if I bring a negative charge closer to it, there is a force of attraction between the positive and the negative charge, and this force of attraction or repulsion, if they are like charges, they repel, if they are unlike charges, they attract, and this force is given by your Coulomb's law. Now when we say electric field, that is actually linked to this force. Now electric field, what is electric field? First of all, we need to understand that electric field is this is a vector quantity. It has both magnitude and direction, and one defines electric field as the force experienced by a point charge. That describes the electric field. Force being a vector, the force experienced by the electric field is also going to be a vector quantity. So the way you can picturize that is, let us say you have a positive charge, or it need not be a single positive charge, it could be, let me see where the eraser is here. So it need not be a single positive charge, it could be some charge density rho, positive charge with volume density rho. Because it's a plus charge, there is a force field around it, and I'm drawing this force field outward because if I keep a test point positive charge here, let's say I'm keeping a test charge here, this is my test charge which I have represented in red, this is my test charge. If I'm keeping a test charge here, this charge is experiencing a force outward. It's going to experience a force away from this positive charge, which is why I'm drawing the force field in this direction. Now this strength of this electric field at this point, because it's a vector quantity, it's actually a vector field. which means it has some magnitude and it is pointed in a specific direction. So if I want to know, let's say at this particular point, I am asking myself the question, what is the electric field? Then the answer to that question is, you have to ask this question, what is the force experienced if I keep a test charge at this point? And that force is nothing but the Coulomb's force, but now it is a test point charge. It's a test unit charge. This point charge, now I say it is a unit charge, which means my electric field is nothing but the force divided by the test charge. If the test charge is, if my test charge is Q, then the electric field is force by Q. I can't keep a very large test charge there. So I would say this limit tending to Q tending to 0. So it's not even unit charge I am saying, it is infinitesimally small charge. So I am using this test charge to measure the electric field. The reason why I want to limit its, find its value when Q tends to 0 is because if I bring another test charge, if I bring this test charge in this force field, I should not be changing the field itself. I should not make this force field repel away because of the presence of the test charge. The test charge is only small enough to measure the field. It should by itself not change the field. I should not let this happen. The test charge should not influence the field. So the force experienced by such a test charge, which is infinitesimally small, it is infinitesimally small because it should not influence the field itself. It should not influence the force field of your original charge. That force is your electric field. So we said a charge that is stationary will be a source of electric field. And the electric field gets defined this way. Now you could have, instead of stationary charges, I can go back and say I could also have moving charges. Charges, the moment you say moving, this could be undergoing uniform motion where it's not accelerated, or it could be an accelerated motion. Just like how a stationary charge a stationary charge can produce electric field, it's a source of electric field. A charge that is undergoing uniform motion actually creates an electric current. We know that electric current is because of the movement of charges. And this, the moment you have an electric current, you have a magnetic field. This was your famous experiment where a current carrying conductor always produces a magnetic field around it. This is an experiment which you have probably seen even in your high school. So the point here is, a stationary charge is a source of electric field. A moving charge which is undergoing uniform motion is a source of magnetic. So it's the charge which is producing both electric field and magnetic field. When it is at rest, it produces electric field. When it moves, it produces magnet. So you can ask me this question, what about permanent magnets? Where are the charges there? Permanent magnet is a source of magnetic field. But the charges are moving microscopically inside the magnet. Right? A magnetic material would have charges moving, which is producing a current and which is a source of magnetic. So the whole of electromagnetics actually deals with electric field which is produced due to charges that are stationary and magnetic field which is produced due to charges undergoing, I'll say, uniform motion. The question you can ask is, what about accelerated motion? That is an answer we will give at the end of this session. At the end of these 3 lectures, the charges that are accelerated produces electric field and magnetic field. In fact, they produce electromagnetic waves. Whole of electrostatics deals with stationary charges, and the whole of magnetostatics deals with charges in uniform motion, the magnetic field produced due to the charges that are in uniform motion, and electromagnetics deals with all of this. When I have charge, when I have an electric field and a magnetic field, if the electric field and the magnetic field is coexisting E and H, electric field intensity is represented by E, magnetic field intensity is represented by the vector H. I already wrote E vector, which is actually electric field intensity. It is a strength force experienced by a point charge when the charge is tending to 0. Similarly, you have magnetic field, and coexisting E and H gives you an electromagnetic field. An electromagnetic field would constitute of an electric and a magnetic field coexisting with each other. If they are existing independently, they can have their own existence independently. I can always have an electric field without a magnetic field. I can always have a magnetic field without an electric field. That is the domain of electrostatics and magnetostatics, which is what we talked about in our previous QEEE session. We talked about electrostatics and magnetostatics. When they are coexisting, you have an electromagnetic field. Now, before going to electromagnetic field, we will revise what we did in electrostatics quickly. So, the first rule, in fact, in any vector, suppose you want to completely, this is a result from vector calculus, that if you want to completely describe a vector, it is enough that you should have knowledge about its you should have knowledge about divergence and curl. If I know the divergence and curl of a vector, I can uniquely define the vector. This is a result from vector calculus. Now, what is meant by divergence and curl? Remember, it's a vector field, which means if this is the space that I am talking about, in this space, my vector could have a specific magnitude given by this length and a direction given by the arrow. At this point, the vector could have a magnitude given by this length, so it is a larger strength, and a direction given by this arrow. In this point, I could have vector pointing in this direction. Its magnitude is given by this length of the line that I am drawing, and the direction is given by the arrow. So, this is how a vector field will look like. So, for example, if I have a plus charge sitting here, the vector field around the charge, the force field around this charge is looking like this, because a unit positive charge, where whenever I keep my unit positive charge anywhere around it, it's experiencing a force away from the charge, and the magnitude of this, so what I have drawn here is a magnitude of the force field at the points given by this red dots. But now if I want to find the magnitude of the field at the point given by let's say these green dots, this is the spatial point at which I want to find what is the magnitude of vector field. Now these green dots are farther from the charge than the red dots, So the field, Coulomb's law, you know, is going as 1 over r square. So the strength of the field has reduced, but the direction remains the same. So this new set of arrows which I am drawing right now are representing the vector electric field at the points, spatial locations given by these green dots. So you see the strength of the field has changed, but in this case the direction has remained the same. So this is an example of a vector field. Because it is electric field due to a charge, it has this particular. If it is a negative charge, I know the electric field is attractive force. So if I pick a set of points around this negative charge and ask myself the question, what is the strength of electric field? I know the electric field is pointed inward because the positive charge is getting attracted to the field, and it has a specific magnitude given by the length of these vectors. Suppose now I pick another set of points away from this, which is farther away. Because they are farther away, the magnitude of the field has reduced, so I will draw shorter arrows, but the direction is remaining the same as in the previous case, and so on. So this is an example of force field. Now what does divergence tell you? Divergence tells you how much is this force field diverging away from a point. How much is it going away from a point? If the conventional or the first principle definition of divergence is, I need to take a surface area. So if I have so I'm trying to define the divergence of a vector A is, I take a surface area, I take a arbitrary surface area around, so this is arbitrary area. I take, so let's say these are the vector, this is how vector A is behaving in this area. I take A dot ds, which means I take a whole surface, I do the surface integral A dot ds, and in the limit, so divergence of a point A of vector A is defined at a point. You are trying to define it at a point. And how do I find the divergence? I need to take the limit of this in the, I need to take the surface integral of this in the limit that delta V tends to 0 divided by delta V. This is divergence of A. And from this comes your Gauss theorem of vector calculus, which tells you that, which is again an extension of what we have written here, the Gauss law for vector calculus, which is essentially nothing but, if I write it as an integral equation, this is the volume integral of divergence of a vector dV. So this is the volume integral, is equivalent to surface integral, closed surface integral A dot ds. This is your Gauss theorem. So divergence is defined at a point. It is a scalar quantity. So divergence, so some physical interpretations of divergence are, it is defined at a point. It is a scalar quantity. It tells you, it gives you a measure of how much does the vector diverges, spreads out. So for example, if I take this force field of the positive charge and I am looking at a surface around this force field, which I am showing as a pink surface now. And if I take A dot ds. Now ds will be a elemental surface somewhere on this, so ds will be somewhere here. The vector A dot ds is A and vector A. So in this case it is vector, it's not vector A, it is vector E in this case, and ds, the direction of ds is the outward normal. So E dot ds, E and ds are in the same direction. So E dot ds is a scalar which is non-zero, and I have a non-zero value for, in this case I have a non-zero value for the divergence of electric field. If I am taking the divergence of electric field around a point charge, it is essentially this, right, from this definition. So A dot ds, instead of A I have E, which is along the outward direction, R direction. Ds is also along the outward direction. So E dot ds will give me magnitude of E. So this is nothing but E, and of course I have to find out what is this vector that represents ds. But that essentially within the limit that if I were to find out the divergence at this particular point, I'll take a surface around it and I'll shrink it. I'll find that out this dot product, this surface integral, in the limit that that volume shrinks to 0. So this pink circle has to shrink to 0 radius. That is your divergence of field. And as we pointed out here, electric field always will have a non-zero value for divergence around a point charge. In fact, the divergence of electric field is nothing but the charge density over epsilon, where rho is the volume density of charge, which means it is the charge divided by volume, and epsilon is the permittivity of the medium. Remember from electrostatics, what is the definition of permittivity? Your electric displacement is related to electric field through this permittivity vector, permittivity, through this permittivity. So this is the permittivity of the medium. The displacement vector gets defined, is related to the E vector through the permittivity. And what I have written here is nothing but your first Maxwell's equation, which is your Gauss law. It simply says that if I can remember the the electric field from a positive charge, I can remember Gauss law, because if I remember electric field that is emanating from a positive charge, it is a highly diverging field, it is completely diverging. So that divergence of the electric field has to of course get related to the charge that is kept here, and it has to get related to what is the medium. So that is where your Gauss law is coming. Now each of these Maxwell's equations, we have 4 equations, all these equations, so let me write that separately. All the Maxwell's equations can be written either in this fashion, what I have done now, which is called as the differential form, or the point form, and it can be also written in the integral form. And last time we discussed in detail when would you use the differential form and when would you do the integral form. To just give you a nutshell of that result, integral form is used when there are discontinuities in the medium, when there are boundaries, when there is a change in medium, that is when you use integral form. Differential form is typically used when you want to solve problems in the same medium. So that is the key result from that. and corresponding to this differential form, the integral form is from the Gauss's divergence theorem, which is volume integral E dot sorry, your suppose I take a volume integral of this equation, that is del dot E dV, that is equivalent. So I am taking an arbitrary volume which is bounded by a surface S, just like how I have shown in this pink line. So this is volume integral. What is the right hand side? Right hand side is rho over epsilon dV. Now from Gauss theorem, volume integral of divergence is nothing but surface integral of that vector. So you have surface integral E dot ds, and volume integral of charge density is charge per volume. So if you integrate charge density, you will get charge divided by epsilon. So this is the Gauss law written in the integral form, and this was the what we wrote here was the differential form of Gauss law. Now to tell you where this integral form is used, why do we need this integral form? As I said, when there are discontinuities or when there are boundaries. Now what is a boundary? I have a separation. On one side I have a medium 1 and another side I have medium 2, where in medium 1 you have parameters mu, epsilon, sigma, mu 1, epsilon 1, sigma 1. Medium 2 you have parameters mu 2, epsilon 2, sigma 2. By the way, this mu, which is your permeability, epsilon, which is your permittivity, you have encountered all these in your electrostatics and magnetostatics, and sigma, which is your conductivity. To remind you, magnetic flux density is equal to mu times H. B is your magnetic flux density, and H is of course your field intensity, which we defined earlier. And where is epsilon coming? It is deciding the relation between D and E, where D is your electric displacement or it is electric flux density, and this conductivity decides how much is the current given that you have a field. Given there is an applied electric field, a charge in that field experiences a force and so it starts moving, and J is your current density. How much is the current flowing? So this is nothing but your Ohm's law, another version of your electric field version of your Ohm's law. So these three are characteristic parameters that characterizes the medium. When we say different media, what we mean is one of these, in fact these are called as constitutive parameters, because they constitute the electromagnetic property of the medium, the constitutive parameters, and these constitutive parameters basically decide how the electric field, the magnetic field, the electric field and the current is going to behave in the medium. So whenever we say media in electromagnetics, it simply means that media is something that is characterized by some specific constitutive parameters. So when I say medium 1 and medium 2, Let me redraw that again because there is no space there now. So if this is my medium 1 and this is my medium 2, this has some mu 1 sigma 1 epsilon 1, mu 2 sigma 2 epsilon 2. The constitutive parameters are different. That is what is different between the media. It's not necessary that all the parameters are different. Even if one of the parameters, say only epsilon is different, but mu and sigma are identical for the two media, even then they are two distinct media as far as electromagnetic properties are concerned. Now, why are we doing this? We are trying to do this to tell you an application where you would use the integral form. So, we said the integral forms are used when there are discontinuity. What is the discontinuity here? The media has changed. There is a discontinuity in the constitutive parameter. Question we are asking ourselves is, if I know what is the E field here as E1, can I tell what is the E field in the second media? I want to know what is the E field in the second media. Given E1, what is E2? This is the question we are asking ourselves. And the answer to this question is yes, I can know, provided I know all the constitutive parameters. What helps you do that? It is the integral form. So how is the integral form helping you do that? Let's pick. So what is the integral form? Surface integral E dot ds is charge over epsilon. I am going to be using this integral form to find E2 given E1. So the way we do that is, because it is a surface integral, I am going to construct a surface, and that surface, I pick a surface, in fact I pick a cylindrical surface because the surface can be anything, partly in medium 1 and another part in medium 2. This is the surface amplitude. One part of the surface is in medium 1, another part of the surface is in medium 2. Now, this relation is, Gauss law is true everywhere, which means it has to be true for this surface also. It is true for any surface. So, I am going to apply Gauss law to the surface that I have pointed out, which means I need to be able to calculate this integral, surface integral E dot ds for this surface I have pointed out. How do I do that? If I look at it carefully, I have a surface area on the top, bottom. The direction of ds vector is the direction of outward normal, which means this is the direction of ds vector here. This is the direction of ds vector here, and on the side surface it is in the direction of outward normal. And this is a dot product. I know the dot product vanishes when the two vectors are perpendicular to each other. They are orthogonal to each other. So what I will do is, for convenience, I will resolve this E vector into something that is orthogonal to ds, orthogonal to the surface, orthogonal to the boundary, and say the one that is, so the component of this E1 vector which is parallel to the boundary is what I am calling as tangential component, and the component of this E1 vector perpendicular to the boundary is what I am calling as E1 normal. So I worked out a tangential component and normal component. I have just resolved my E1 vector into a tangential component and normal. And if I calculate this surface integral, this surface integral is the sum of 4 surface integrals. If I call this as surface, in fact sum of 3 surface integrals, S1, the side surface S2 and the bottom surface S3. It's a sum of surface 1, top surface, S2, side surface, bottom surface S3 of the cylinder. That is my left hand side. My right hand side is the charge inside this surface divided by epsilon. Now if I calculate, if I want to find out what is this in the blanks, on the top surface my E field is having a tangential component and a normal component. Let me draw the normal component in green and tangential component in red. So this E dot ds, E vector is the normal component, the green vector, and this blue vector, I have to take the normal component. I have to take this dot product of these two vectors. So this is the E1 normal component and they are in opposite directions. So the result of this is E1 normal component, and I have integrated, so this is E1 normal component in the normal direction plus times ds in the normal direction. So instead of writing all that, I am just writing the result. E1 normal, if I integrate that area let's say is A, where this area of this top surface and bottom surface I am taking as A. So this is E1 normal A. They are in opposite direction, so they have to be minus E1. I am also going to do one more thing. Instead of taking the side surface, I am going to calculate the whole thing in the limit as the height h of the side surface tends to 0. I am calculating this integral the limit that this cylinder height actually reduces to 0, which means I am calculating the integral on the side, this integral on the side, the limit that side itself is reducing to 0, which means nothing happens to the top surface because that is intact, but the side is reducing to 0, which means the second integral contribution S2 is 0. Now the third integral is the bottom surface. In the bottom surface, I do not know what is the electric field in the bottom surface. Let me call that electric field is E2. But I know very well that E2 can also be resolved into its normal component and its tangential component. And since the surface ds is in the downward direction, I know that this red, which is the orthogonal component, the tangential component, has no role to play. It is only this, it's only this normal component of E2, which is E2n. Again I take this integral. Now you see E2 as well as ds are in the same direction in the bottom surface. So this is E2n times A is equal to the right hand side. Now what should be the right hand side? Here is where I will have a problem. Now the right hand side says it is a charge enclosed divided by epsilon. I have two problems here. I do not know what is a charge enclosed. I do not know whether there would be a charge enclosed. Second problem is, which epsilon should I take? Should I take the epsilon corresponding to E1 or should I take the epsilon corresponding to E2? If I write this way, I don't have an answer to that question. First confusion is I don't know which epsilon to pick. Because my h has reduced to 0, the surface is infinitesimally small. One side of it is in medium 1, other side of it is in medium 2. Each media has different epsilon. So the way to solve that problem is to say that I will smartly not use this epsilon here. I will smartly say use the Gauss law, not this way, I will do it this way. I will use the Gauss law, epsilon E ds equal to q, or in other words I can write d dot ds equal to q. What is the difference by bringing it to the left side? The difference is I just have to put, now this is for epsilon 1 because my epsilon here went to as a product here. So when I am picking E1, I will choose that epsilon 1. If I am picking E2, I will choose epsilon 2. So I am essentially writing in terms of D vector, not E vector. So that first problem is resolved. I still don't know what is the Q. Now what is the Q that we are talking about? Suppose this is medium 1 and this is medium 2. My surface is actually a surface, one part of it is on top, the other part is in bottom. I mean the bottom surface is in medium 2, top surface is in medium 1, and I am trying to find out in the limit h tends to 0 what's happening. In the limit h tends to 0, the charge that I am talking about is the charge that could have accumulated in the surface, which is shown as pink here, which means this charge is the charge in the surface, right? So if your media is such that, for example, if it is, we will talk about media later. At this moment, let's say if the charge is 0, if I just have the charges as 0, then if this charge is 0, then E1 normal epsilon 1 E1 normal equal to epsilon 2 E2 normal, which means my E2 normal is nothing but E1 by epsilon 1 by epsilon 2 E1 normal. I have found out what is E2 normal given my E1 normal. So I have partly succeeded in finding out what is the value of E2. I got the normal component. I still have to find out the tangential component, which I will find out from some other boundary condition. But this is the way we have used the integral form. This is one application of your integral form where you use this integral form to find what are known as the boundary conditions. You already got one boundary condition which says that the normal component of E vector and the normal component of E vector in one medium and the other medium are not equal. The normal component differ by this ratio epsilon 1 by epsilon 2 depending on the permittivity. If I write in terms of D, it simply reads as D2n minus D1n. In fact, this is equal only if the surface charge density is 0. If there is a surface charge, I actually need to find that surface charge density also. So if your surface charge is 0, we will talk later about media which will have this, which will not have this, but if the surface charge is 0, this is your boundary condition. So this was about the first Maxwell's equation, Gauss law. Talked about integral form, differential form and so on. So from the beginning, if I take a quick look, what did we do? We talked about electric field, magnetic field. We talked about what is divergence. We still haven't talked about curl, but I gave you an example where for a vector which is diverging, which is an electric field vector. We talked about Gauss theorem, talked about Gauss law, and we talked about the integral form of Gauss law. We also talked about one application of integral form of Gauss law, which is your which is your boundary condition. We also talked about permeability, permittivity and conductivity. I am going to take a break now and open the session to questions to see if you have any specific questions until now. Okay, so there is a question here, will the divergence apply for magnetostatics? We are going to be talking about that now. So I have a question here, will the divergence be applicable for magnetostatics? So I am going to talk about magnetostatics right away. So that answer will come in another 5 minutes. Okay, if there are no questions, I will continue here. Before we go to magnetostatics, one more thing we want to do, because we just said that a vector is completely you can completely describe a vector from its knowledge about divergence and curl. So we talked about the divergence of electric field, so we better talk about the curl of electric field. So the next thing we are talking about is curl of electric field. To remind you, what does curl tell you? Curl tells you how much the extent of rotation. It tells you how much is it rotating. It also tells you the direction of rotation. So curl is a vector quantity, unlike divergence, which was a scalar quantity. Now if you take electrostatics, before we do that, I will give you an example where the vector curls. So just like how we drew a boundary for a diverging field, let's draw a boundary. Let's draw the space, a rectangular space. Let's say my vector at, so I am with green dots, I'm going to mark some spatial locations. I'm just going to mark some spatial locations. I'm just locating some points in the space. And let's say I have a meter which measures the magnitude and direction of this vector, some vector. It could be a velocity vector, it could be a force vector, some arbitrary vector. And let's say I'm going to measure the magnitude and direction of this vector. So, and if I do that, that meter is indicated. And again, as in the previous case, my arrow is going to show the direction of the vector. The length of the line that I'm drawing is showing the magnitude of the vector. And let us say it is doing this. So unlike in the previous case where you saw all the vectors coming out, I have specifically chosen an example of a vector field here where all the vectors are rotating. If you see in this part, all the vectors are rotating in one direction, whereas in this part, vectors are rotating in some other direction. So if vectors are doing this way, typical example is a whirlpool. In your river or in your stream, there could be specific locations where the velocity vector of water is actually rotating, which kind of traps something that is falling in it. That's a whirlpool. So velocity vector of water in a whirlpool is a classic example where that vector field has some curling, some rotating effect. So this is an example of a vector field, curling field, vector field which has curl. In the earlier example where you take this example where we talked about the electric field of a positive charge, vectors are not rotating, they are just diverging away. So this is a case where I can say curl is actually 0. It's not rotating, it's just diverging away. So this is a vector field. This is an example of a vector field. Electric field coming out of a positive charge is an example of a vector field where it is diverging, but there is no curl. Curl is 0 because it's not rotating. So curling vector field example is velocity vector in a whirlpool. You want to see a whirlpool at your homes? You have whirlpool at your homes. Where? Washing machine. You put it on rotation, water is rotating, the velocity vector is actually curling around the center, right? So these are all examples where they are curling. But clearly, what I will just repeat what I said. If I just take this vector field, that is the electric field due to a point charge, there is no rotation. In this case, there is no rotation, which implies curl of E is 0. Curl of E is 0 for electrostatics. And this is your second Maxwell's equation for electrostatics. This is not true when the magnetic field, when the electric field, when you have time variation essentially. But as far as electrostatics is concerned, curl of E is 0, everything is static, electric field cannot curl. Okay. We will come to this modification in a bit. Faraday's law actually modifies this. So, we will come to Faraday's law, but before that we will write the integral form of this equation. And the integral form of this would be, okay, the way the integral form comes out is line integral. Suppose I take a surface integral of curl of E, I am taking the surface integral. So, I am taking a surface, let us say this surface, which is marked in the inner black line of this curl of E, ds, and the right hand side is zero, because the right side of this equation is 0, and surface integral of curl is nothing but line integral of E dot dl. We discussed this in the first, this is your Stokes theorem. We use the Stokes theorem to go from here to here, line integral E dot dl is 0. So, this is the integral form of Maxwell's second equation in electrostatics. This is your Maxwell's second equation. We will quickly see what is the application in terms of boundary condition. How does this mean? What does this mean as far as the boundary conditions are concerned? Boundary conditions, not equations. So, again we will construct our boundary, medium 1 and medium 2, and because it is line integral, I will not take a surface, I will take a loop. The loop is taken in such a way that one part of the loop is outside in one medium, the second part of the loop is in the, one part of the loop is in the second medium. As in the previous case, we have mu 1, epsilon 1, sigma 1 characterizing medium 1, mu 2, epsilon 2, sigma 2 which characterizes medium 2. And again as in the previous case, we have E1 in medium 1 which has a tangential component E1 t, we wrote it as E1 tan, same way we will write it as E1 tan, and a normal component which is E1 normal. Our objective, earlier we could find something about the normal component, but to be able to describe the vector completely, I would need the tangential component and the normal component. So, the attempt now is to find out what is E2. Specifically, I want to find out what is the tangential component of E2. I already have information about the normal component of E2. I want to know what is the tangential component of E2. Now, the way to do that is I have to calculate this line integral. Line integral means I have to integrate this vector over this closed, this is the direction of dl here, this is the direction of dl here, this is the direction of dl in this case, and here my dl is in this direction. So, it is actually a sum of 4 integrals. First integral along this horizontal, second along the vertical, third along the horizontal, fourth along the vertical. But as in the previous case, I have ambiguity only at the boundary. I know very well what is happening outside in the medium, first medium and in the second medium. So, when will I reach the boundary? In the limit that, let us say I take this height as, or this height, this length as h, I will calculate, I will apply in the limit h tends to 0, I will apply this boundary, I will apply this Maxwell's integral equation E dot d, which means, and as I said, this is the sum of first integral plus, so if I say this is 1, this is 2, 3 and 4, this is 1, 2 plus integral 3 plus integral 4 equal to 0. Of course, I need to write down what these integrals are, but what I can say straight away is that when I apply the condition that delta h, when h is equal to 0, the second integral will reduce to 0 and the fourth integral also reduces to 0. I am left only with the first integral and the third integral. And if you look carefully, the first integral tangential component is along dl and I am integrating over this entire length. And what is that entire length? That entire length would correspond to, let us say the total length is L. So this is E1 tangential times L. The third integral, you have tangential component is along the right side, dl is along the left side. So the integral is minus E2 tangential L equal to 0. This would imply E1 tangential equal to E2 tangential. In our earlier boundary condition, we had an A, and that A reduced to 0 because this is 0, but here in the presence of Q surface, make sure it reads as E1 normal minus epsilon 2 E2 normal is Q surface by area, which is your surface charge density. This would be the case if I had a surface charge density, just to correct that. Of course, in this case, there is no right hand side, so you don't have a problem, simply because the curl of E is 0. So E1 tangential, which means the tangential components of E is continuous. Continuous meaning, if you had a specific component here, the component here is also the same. So if, let us say for example, let me take an example problem. Let us say this is my boundary. I have electric field, let's say, which is 10 units. Let's say electric field E1 is, magnitude of E1 is 10 volt per meter, and it is making an angle, say for example 30 degree. This is 30 degree here, which means my tangential component is, and let's say its electric field is along the same plane. The way I have drawn the electric field is along the same plane of the board, and this is my boundary. And let's say this has mu 1 epsilon 1 sigma 1, mu 2 epsilon 2 sigma 2, and let's say this is just air glass interface, which means one side is air, the other side is glass. This is air, this is glass. I know that the magnetic properties of air and glass are not different, conductive properties are not different. So I am going to say sigma 1 is sigma 2, mu 1 equal to mu 2. All what is different is epsilon. Now epsilon 1 is epsilon naught times the relative permittivity of 1. Epsilon 2 is your epsilon naught times relative permittivity of 2. With that information, the question is, given this E1 magnitude of E1 is this, given that let's say this is the xy plane, and let us say E1 is in the xy plane. I have an electric field applied in the xy plane with this angle that I have marked, this angle as 30 degree, this angle is 30 degree. Question is, find the electric field in glass. Find the electric field E2 in glass. I want to completely describe the field, magnitude and direction. Would it be the same? Would it be different? What is it? So how do I solve this? I resolve this into tangential component and normal component. Now remember, tangential and normal to what? I am resolving this tangential and normal to the boundary. So the first step for any solving any boundary value problem is resolve E vectors along E tangential normal to the boundary. This is a simple enough problem. I have taken the boundary here. This is my boundary. Boundary is along the YZ plane. Now if this is my E vector, then what is tangential? It is 10 cos 30. Normal is 10. So I am going to write this separately here. E1 tangential magnitude is 10 cos 30. So this is sin 30 is 1 by 2, cos 30 is root 3 by 2 volt per meter. And E1 normal magnitude is 10 sin 30, which is 5 volt per meter. So my vector E1 is actually 10 root 3 by 2 along the AY direction plus 5 along the AX direction. And AY direction is the tangential component because that is parallel to the boundary, and this is the normal component. This is a case where the vector is in this plane, but if the vector had a z component also, that's also not a problem. If this plane, for example, this is the plane of the boundary, this is the YZ plane, and if my vector is pointing this way, the way I would resolve is, this is my YZ plane, so this would be my x axis. So along the x axis is the normal, and whatever is along the component of this vector along the YZ plane, that is the tangential component. The tangential component is your y plus z put together. Okay. So in this case, the boundary is in the xy plane, sorry, YZ plane. So component along YZ is the y and z is the tangential component. So if the vector was, instead of 10 root 3 by 2 ay, if that had an az component also, then that whole thing would be your tangential component. So this is on the first side. And what are our boundary conditions? And let's say there are, the boundary it is given that there are no charges. Even if there are charges, we can take care of that. How do we take care? We need to find the charge density and substitute the surface charge density here. In this case, I am giving you that the charge density is 0. So I know the boundary conditions from my first two Maxwell's equations. The tangential component in E1 tan is equal to E2 tan. That's what we proved just now, which means E2 tan magnitude of that is also equal to 10 root 3 by 2 volt per meter. E2 normal is equal to, go back to the first boundary condition. What was the first boundary condition? E2 normal is epsilon 1 over epsilon 2 E1 normal. Epsilon 1 over epsilon 2 E1 normal. Epsilon 1 is air, which is epsilon 0. Epsilon 2 is glass, which is epsilon 0. Let's say refractive index of glass is 1.5. So epsilon is 1.5 square. Let's say that is information is known to you. Epsilon R2 is that of glass, is the refractive index of glass square. Times 5, because E1 normal is 5. So this is 5 over 2.25. And this much volt per meter is, I'm trying to get the exact number for what is 5 over 2.25. So let me do this. 5 over 2.25 is approximately 2.2 volt per. So what has happened, what the point I'm trying to make is, in the first case, the vector was, you see 10 units here, it's making an angle 30 degree. So I've actually drawn an angle 45 degree here. Let me draw a 30 degree angle here. So this is my y-axis. In fact, I made a mistake. My normal component, if my x direction is this, my normal component is opposite to the x direction, which means I need to correct this as my x direction. In the x direction, I need to make a correction. It is along the minus x direction. If I have chosen this as my x and this as my y, my vector is in the minus x direction. So this is my y and I have chosen my x here. My vector was at an angle this angle was 30 degree. So it had some x component given by this blue line and its y component was given by this green line. This was my E1 vector. This length was 10 root 3 by 2 and this is 5. Now E2 has an x component, tangential component equal. So the tangential component of E2 is remaining the same. So I'm drawing E2 now. The tangential component of E2 is remaining the same. I should make the same correction here. This is minus, I should make the same correction here. This is minus 2.2. So the tangential component remains the same. Normal component has become minus 2.2, which means instead of 5, I have only 2.2, which means my resultant E2 vector, what has happened to that? The resultant E2 vector has changed its magnitude and direction. This was my E1 vector. This is my E2 vector. It has actually turned its direction. So if my E1 vectors were represented like this, I'm just drawing a parallel to this. My E2 vectors, so the E1 vectors are represented like this at the boundary. What is happening to the E2 vector? In the second medium, it is doing this. Of course, this is the surface of separation. This is air, this is glass. And this phenomenon is familiar to you. Even though you have not learned in the context of electric field, this bending of electric field is what you call as refraction. bending of light. If it is light, it is refraction. So what we have been able to work out, totally apparently different phenomenon of refraction is what we have explained. What has happened is it is bent this way. Now let's just go ahead and try to see the same things for what is happening in the case of magnetostatics. Oh, before even we go to magnetostatics, we need to modify this curl of E equal to 0, we need to modify it for time varying fields. So for time varying fields, what we need to, so when I say time varying fields, it means that the electric field and magnetic field is varying as a function of time. Whenever you have a time varying magnetic field, when the magnetic field changes as a function of time, you have an EMF induced. This is your Faraday's law. The Faraday's law tells you that this actually comes from should have talked about Oersted discovery that whenever you have a current carrying conductor, it produces a magnetic field. So the quest was, can the reverse happen? A current carrying conductor is producing a magnetic field. Can a magnetic field under any circumstance produce current? Turns out that a steady magnetic field cannot produce current, but a time varying magnetic field can produce current. It can induce EMF, and that is your Faraday's law. Now, how do we now express it mathematically? Now, this was Oersted's discovery, and the induced EMF, VEMF induced, is found to be proportional to, it increased whenever the change in flux, the rate of change of magnetic flux changed. So, it was proportional to minus d phi by dt. So, induced EMF was, this is your Faraday's law, which you have learnt in your school also, where phi represents the magnetic flux. If you have a coil, then it depends on the number of turns in the coil times the flux induced in each coil, that is a total flux. Now, from our basic understanding of what is electric potential, we can write the potential as E dot dl, and that is minus d by dt of the flux psi. Now, this negative sign you would have learnt in your school that this is your, this negative sign is to account for Lenz's law, which says that the induced EMF produces a current such that it opposes any change. If the flux is increasing, the induced EMF is produced in such a way that the current due to the induced EMF produces a field opposing the change. There was a change because of which there was an induced EMF, and the current due to the induced EMF produces a magnetic field which opposes whatever change produced it. And from the definition of flux, we know flux is nothing but surface integral of B dot ds. B is, as defined earlier, is the surface integral. B is the flux density. So this gives E dot dl is minus, I will write del by del t because this could be a function of position as well as time, B dot ds. And if B is the only thing that is changing with time, then line integral E dot dl is negative surface integral del B by del T dot ds. Now even here in your electrostatics, in your Faraday's law, you would have learned that B can change when the magnetic field changes, the coil remains stationary. That's what happens in a transformer. Coil is stationary. It's just that the magnetic field is changing as a function of time. You're applying an AC, so magnetic field is changing as a function of time. That kind of induced EMF you call as transformer EMF. Or you could have flux cutting EMF, in which case the coil is moving. Here coil is stationary. We will not get into the details of that, but those are what, the two kinds of changes that can happen. Where the coil remains stationary, flux changes, the resultant EMF is what you refer to as transformer EMF. Field remains the same, coil is moving to and fro, there is a mechanical movement of the coil because of which there is an EMF, that is your flux cutting EMF or motional EMF as it is called. So this is the statement of Faraday's law. Now how do I write it in the form, this is actually the integral form of Faraday's law. How do I write it in the point form? If you go back and look at it, curl of E dot dl was nothing but curl of E. So I apply Stokes theorem again. So I call this as, this is curl of E and this is minus del B by del T, because I replace this with surface integral curl of E ds. These two are identical. So surface integral curl of E ds is the same as surface integral del B by del T. These are the same surfaces we are talking about. So your curl of E is minus del B by del T. This is your Maxwell's second equation, your curl equation. When you have a time varying magnetic field and the magnetic field is changing as a function of time. Of course, in magnetostatics and electrostatics, where everything is static, nothing is changing as a function of time, this right side reduces to 0, so you get curl of E is 0. You go back to your original Faraday's law. But point to remember is that this is the correct form which accounts for time varying magnetic field. So what we have done until now is Maxwell's two equations. First equation, which is your Gauss law, del dot E is rho over epsilon and curl of E is minus del B by del T. We wrote down the integral forms also, and we wrote down how is this integral form useful. Just now we calculated what is the expression of a total electric field by knowing the boundary conditions. Now we move on to complete description of magnetic fields. Just as I mentioned a minute ago, a current carrying conductor produces a magnetic field. Now current carrying conductor is, as I discussed in the beginning of the session today, a current carrying conductor has charges moving with uniform velocity, and charges moving with uniform velocity, we just in the beginning of the session said they are sources of magnetic. So if the current is being carried in this direction, you have a magnetic field. So I have a current in this direction, in the direction of, let's say, the direction of the pen that I am using, my magnetic field is curling around it. If I draw the cross section, let's say current is being carried into, the moment I put this mark, it means I put an into mark, it is into the plane of the board. So it is into, and around this I will have magnetic field lines which is circulating around this. If my current is in this direction, again I have magnetic field lines. My circles are not uniform, but these are uniform magnetic field lines. What I have drawn is the magnetic field H, and this out of into the plane. So this is telling you the direction of current. Just like Gauss law described how much is the divergence of electric field from a charge, you have Ampere's law describing how much is the curling of the magnetic field around the current carrying conductor. Conductor is moving this way, current is moving this way. I have a magnetic field around the conductor, and the strength of the curl, how much is it curling, is decided by the strength of the current. Just like how much is the electric field diverging is decided by the charge located, which gave you divergence of E is related to rho, the strength of the curling magnetic field is decided by how much is the current. So that gives you the statement of Ampere's law, which tells you that line integral H dot dl, because it's curling as a line, it's curling around. So the loop integral H dot dl is nothing but, it has to depend on the charge, it has to depend on the current. So if J is my current density, my current is surface integral J dot ds. So this is my Ampere's law. Line integral H dot dl is surface integral J dot ds. This is actually representing the current. I can write it in, this is my integral form, I can write it in point form by saying that curl of line integral H dot dl is, use Stokes theorem to say this is curl of H ds, right side remains the same, J dot ds, the same surface we are talking about, so curl of H is J. So these are your integral form and point form for Ampere's law. What about the divergence of, as somebody asked, divergence of magnetic field? Is it diverging? The answer is no. Simply because whenever you have a current, the magnetic field curls around it. It doesn't come out. It's neither acting, your current is not a source or sink of magnetic field. Whereas a charge, a positive charge is a source of field. A negative charge can sink field, it can take in field. Whereas a current can never take in magnetic field or give out magnetic field. All what it does is it curls the magnet. It produces a magnetic field, but it curls the magnetic. So for the same reason, del dot H is 0, because no divergence. Another way of saying it is that you have no magnetic monopoles, because only when you have monopoles, only when you can isolate a positive charge, can you have diverging electric field. Whereas if I have a magnetic field, you think about a north pole and a south pole, you will always have the field completing a loop. You will always have this field completing a loop. You can never find a north pole with just diverging. This is a situation you will never find, because there is always a south pole and this will always complete a loop. What does it mean? If I take any surface, I will have field entering and field leaving the surface. The moment I have field entering and field leaving the surface, my volume integral tends to 0. Net flux outward is 0, because whatever came in left. So whenever you have closed fields, your divergence is always 0. So that completes all Maxwell's equations. You can work out similar boundary conditions for magnetic field. This will give you a boundary condition for the tangential component, because the line integral gave you something for tangential component, and you will get something for the normal component from this. What is the corresponding, you have the corresponding integral equation. You can write the corresponding integral equation here for this, which is integral of, this will be h dot ds, just like how you had d dot ds, surface integral of h dot ds is 0, similar to how you wrote for the electric field. You wrote that E dot ds is q, the right side is 0, so here h dot ds is going to be 0. So just to sum up what we wrote down, so before we sum up, this is surface integral h dot ds is 0, which will give you h1. Remember, the surface integral gave you normal boundary conditions for the normal component, because you took a surface and you took a volume and you had a cylindrical volume and you talked about calculating the surface integrals. So this gave normal component h1 normal will give me h2 normal, which is the same as b1 normal is equal to b2 normal, because right side is 0, so both are going to be the same. And the tangential components is going to give me h1 tangential minus h2 tangential is going to be, it's going to be related to your J, it's going to be the surface current density. Just like how you had the surface charge density, you will get the surface current density. So this completes the magnetic field also. So putting all this together, all your 4 equations would be curl of divergence of E is rho by epsilon, curl of E is in considering magnetostatics, curl of E is minus del B by del T, which you can write as minus mu del H by del T. Curl divergence of B is 0, or divergence of H is 0, curl of H is J. This is your law, this is your Faraday's law, this law doesn't have a name, and this is your Ampere's law. Then why do you call it as Maxwell's equations? Maxwell has not contributed in any of these things. You call it as Maxwell's equations because Maxwell made a small correction to Ampere's law so that it is self-consistent. That's what we will deal with now. Before we deal with that, I will take some questions which have come up here. First question, it says, will the divergence be applicable for magnetostatics? We have already answered, yes, it is applicable for magnetostatics also, except that the divergence of H is 0. other question is, can you tell me an example of dielectric case? So I think the question is being referred to the boundary. So the example that we worked out, air and glass, we said one medium is air, the other medium is glass. This is a case where this is a dielectric and this is also a dielectric. This is a case of dielectric boundary. I hope that answers. Tomorrow first thing we will talk something about these media to tell you what decides a medium is dielectric, what decides what is a dielectric, what do we mean when we say it's a dielectric, or what decides a media, what decides to say okay media is a conductor. What are the physical significance of divergence and curl? I think I explained that already, maybe you missed that. So that's the pictures that I was drawing for you. This picture, that pink line shows that, if I take a surface, if the vector field is around a point is coming out, it's the direction of the vector field in that space is in such a way that it's all directed outwards from a point, then it has divergence. I'll give you one more example. Suppose in the space I have vector fields like this. Vector fields like this. Is it diverging? Is it curling? What is it doing? What can I say about the divergence? And let's say this is a vector field A. It's definitely not coming out from everywhere or from a point. So which means this divergence of A is 0. It's definitely not curling, rotating, because it's just going parallel, which means this is an example for a case curl of A is both divergence and curl is 0. Show you another example. Let's say I have something like this. I'm just drawing some arbitrary vector field. This is an example where, at this point it is diverging out. At the same time, it is spiraling also. So this is an example where divergence is not equal to 0, curl is also not equal to 0. We saw an example here, the other case, this is the case where it's only curling. So here divergence of H is 0, but curl of H not equal to 0. And our electric field in the electrostatic case was an example where the divergence is non-zero, curl is 0. So I hope that answers. So I have another question. In what way can you treat air as a dielectric? So I will give you an answer to that tomorrow when we discuss the properties of media, because as I said, tomorrow we are going to talk about in our agenda, tomorrow's class is going to be talking about dielectric, lossy dielectric. So we'll talk more about media in tomorrow's class. I hope you get an answer tomorrow. Is there any other question? I don't see any questions on the window. So I go ahead. So this Maxwell's equations are not complete if we don't talk about what is known as the equation of continuity. Okay. You see, Faraday's law talked about moving magnetic field producing an electric field. Ampere's law talked about, so Faraday's law was talking about magnetic field producing electric field. Ampere's law was talking about current producing magnetic field. You can derive Ampere's law, you can derive Gauss law, assuming that you take Coulomb's law and Biot-Savart's law as postulates. But we will not go into all that. That's all there in the previous session. But the point is, Ampere's law talks about what is the strength of the magnetic field due to a current. Now there is no law which is, at least in the what we discussed, which talks about electric field producing current. What is the relation between the electric field and the current? Because whenever there is an electric field, there is a force for the charges to move, and because of that force the charges start moving, produces a current. How is that related to electric field? We said Ohm's law, we say current is directly proportional to the field, but there is something that has to relate to the rate at which the charges are moving, and that is your equation of continuity. Only then the complete cycle is over. H producing E, J producing H, E producing J, so that we are completing the story. Now the way to do that is simply conservation of charge. So let us say I have a region where there is some charge Q which is enclosed in a volume V. Okay, I have a region where there is some charge accumulated, and let us say that charge is allowed to move, it is allowed to come out of this medium, just coming out of the medium. Think about it as some source of radioactive source giving out beta particles, which are electrons, which is giving out some current. Now let us say J is my current density. What would be the conservation? So what will be the law of conservation of charges? Time rate of change of charge must be the outward current. Rate of flow of charge is current. That's all what I have written here. How do I express this now? Outward current I am writing as I out. I out, if J is the current density, current is surface integral J dot ds, and that should be equal to the time rate of change of charge. Time rate of change of charge is nothing but dq by dt, and since the charges are flowing out, I put a negative dq by dt. So I have this relation, surface integral J dot ds is minus, sorry, there is no integral here, this is minus dq by dt. Now I make use of Gauss theorem. Gauss theorem says that surface integral J dot ds is nothing but volume integral del dot J ds dv. I can replace a surface integral with a volume integral so long as I replace the vector with its divergence. Is minus, to make it look uniform, this charge I am going to write it as volume integral rho dv, where rho is your volume density of charge. So this would mean these two volumes are identical. So my del dot J must be equal to minus d rho by dt. Del rho by del t, because I could have rho changing as a function of time, v changing, rho could be a function of space and time. So del rho by del t. This is my equation of continuity. This tells me what is the divergence of current given there is a flow of charge. This is still in the very much in the domain of statics, magnetostatics, because this del rho by del t, well, there is a time varying component for charge. Charge is flowing here. So the point we are making is all this should be consistent with this other rule we got, that del dot j is minus del rho by del t. All of them should be consistent with each other, because we are talking about the same electric field, same magnetic field, same current which is creating a magnetic field, same current which is due to the flow of charge. It is the same charge which can give you this divergence. All these quantities are the same actually. What Maxwell found was that these two were not consistent. That is Maxwell's contribution. He fixed the inconsistency. So first let's see what is the inconsistency. Why do we say there is an inconsistency? We have curl of H is J and divergence of J is minus del rho by del t. What is inconsistent about it? We'll figure out in a minute. Suppose I take the divergence of this equation, because I want to basically find out if I take the divergence from this equation, is it working out to be the same? I know the divergence from the second equation. From the first equation also, if I calculate divergence, is it working out to be the same? So I take the divergence of divergence of J, and the divergence of J is minus del rho by del t. This is true from the equation of continuity. What about the left hand side? We just discussed what is the physical significance of divergence and curl. Now you are saying take a vector, find its curl, which means find how much is it rotating, and then find its divergence. Find how much that rotating vector is diverging away. And that answer is clearly 0, because a rotating vector is rotating, it is not diverging away. Right? Because this curl tells you how much is the vector by which the vector rotating. And that is not diverging away. So this left hand side unfortunately is 0. And this is the inconsistency, because it simply means that rate of change of charge is 0. That is not the case always. I can have a charge moving, and when I have a charge moving, it means that Ampere's law is violated, because I can't say the equation of continuity is violated. This is always true, because charges are moving out, that is producing a current. Equation of continuity is telling you only that the charge is conserved. So violation, so somehow this law, this is not correct, right? There is some mistake somewhere, and it is this inconsistency that Maxwell identified, and he fixed this inconsistency by saying that, look, this curl of H is actually not equal to J, it is J plus some JD, so that when you take the divergence of curl of H, it should actually be 0, and so this divergence J plus divergence JD is actually coming out to be 0. So this divergence of JD is actually minus J, and using this divergence of JD is del rho by del T. So he added a new term such that when you added the divergence of that new term with the divergence of J, you ended up with a 0, because this is always 0. This term he added such that the net is 0, and the magnitude of that term he calculated is del rho by del T. So divergence of JD is minus del by del T rho. Now I know from del dot D is rho, so I can substitute this as del dot D, which means my JD, sorry, this is my plus, my JD is the divergence are thrown away, it is del D by del T. So he fixed the Ampere's law as curl of H equal to your regular current density plus del D by del T, so that when you take the divergence of curl of H, the right side is divergence of J plus divergence of JD, and that JD is minus del J, which is divergence of J, which is del rho by del T. Now it becomes consistent. And he modified Ampere's law to say that this is J plus del D by del T, and that was Maxwell's contribution. Details of these we discussed in the previous session. So nothing changes except that for the case of time varying fields, your curl of H is J plus. So it's physically, it simply means that the way H curls is not only decided by how much is the current flowing, it is also decided by how much is the field, electric field changing with time. So it means, we said earlier that as for a current carrying conductor, there is a magnetic field around it, and the way it curls is decided by the strength of the field. The addition is that in addition to the strength of the field, it is also decided by del D by del T is nothing but epsilon del E by del T. It simply says that it also depends on, if there was a time varying electric field, it also depends on by how much is what is the time variation of this electric field. That is the additional contribution, that is the physical secret. The curling of H is not just decided by the current, it is also decided by the field. So which is very logical, because curling of E is decided by the time variation of H, curling of H is decided by time variation of field. So they become symmetric, and this is how all these with the corrected Ampere's law gets called as the Maxwell's equations. So we stop at this point now. Tomorrow we start with the solution for the Maxwell's equations with the wave equation, and we talk about the different kinds of media. So if there are any questions, I am ready to take that. I see, how do you justify current flow through a capacitor? So you have already answered the question. The current flow through the capacitor is justified through this del D by del T. So in a capacitor, by asking that question, you have already answered the question. There is electric field from the, let's say this is the plus plate and minus plate, there is an electric field. So if I have a time varying field, there is del D by del T happening here, because the electric field changes as a function of time, and the displacement current, this is what we call as a displacement current, that flows through the capacitor, which is providing a continuity. I have another question which says, why is there a negative sign in calculating the electric field normal to the boundary conditions in the curl of electric field? So where is the electric field, let me just go back to that point. Suppose you are referring here. So this is where we use, probably you are referring to this negative sign. That is because I assumed my electric field tangential component here and my dl was in the opposite direction. So E dot dl should have a negative sign. Any other questions, please ask. So if there are no more questions, I will stop the session. Please feel free to ask your questions in tomorrow's session regarding anything that we learned today. We'll see you tomorrow again at 2 o'clock.